Hello everyone. As part of our assignment in physics, in this video I am going to be discussing about laser physics. So laser physics is a branch of physics that deals with all the stuffs about laser. Laser is a very common term. People use laser in their day-to-day lives regularly, but most of them don't know about the meaning of laser, the production, the use, the type and everything. So in this video I am going to be giving you a detailed view on laser. So let us first know what actually laser means. So if we introduce laser by converting it into the full form, we get light amplification by stimulated emission of radiation. For L we have light, A stands for amplification, S for stimulated, E for emission, R for radiation. So simply by this definition we can say that light amplification, which is obtained by stimulated emission of radiation, is termed as laser. What does actually light amplification mean? Light amplification means the process of multiplying or intensifying the light. The increase in power of light, the increase in intensity of light, all comes under light amplification. In laser we obtain light amplification by stimulated emission of radiation. Radiation is a very broad term, but in brief sense we can say it as a form of energy. So radiation is a form of energy. As we know, light travels in forms of photons, and the collection of these photons is known as radiation. When we are able to obtain stimulated emission for this radiation, we are able to obtain actually laser light. About emission and about stimulated emission we are going to be discussing in brief in the later part of this video. So first of all we need to know why do we need laser. So actually if we break all the light sources we can briefly find these three sources of light, namely conventional light sources, LED and laser. And if we compare these three light sources on the basis of these three fundamental light properties, we can come to a conclusion that laser is far more superior than conventional light sources and LED. So first let us describe what is spectral chromaticity and coherence. As we know, for the light to travel we need some energy transmission. Energy transmission may be continuous or discrete. By discrete energy transmission we mean the energy transmission from one level to another level is in certain intervals, but in continuous energy transmission the energy transmission is following a continuous curve. It is not in a break or in a certain interval. And chromaticity deals with the fundamental property of frequency. A light source may be either monochromatic or non-monochromatic. By monochromatic light source we mean to say that the particles in the light particles coming from the light source are having the same frequency, but for monochromatic light source the particle coming from the light source are having a different frequency with each other compared to each other. Now coherency is also divided into two types. Light source is either coherent or non-coherent. By coherent light source we mean the particles in the light source, particles which are responsible for the light to travel, are in phase with each other. But by non-coherent light source we mean to say that the particles that are responsible for the light to travel are not in phase with each other. In other words we can say that they are not in ordered condition. So let us see which of these light sources are having which spectra, which chromaticity and which coherence. So conventional light sources, for common example being incandescent lamp. The conventional light sources have continuous spectra, they are non-monochromatic and they are highly non-coherent. If you see about LED lights, that stands for light emitting diodes, as you all know. They have discrete spectra, they are monochromatic but they are non-coherent. And if we say about laser, which we are especially talking about in this video, they have discrete spectra, they are monochromatic and they are highly coherent. For our nice quality of light production, We need this to be discrete spectra, this to be monochromatic, and this to be coherent. All these conditions are fulfilled by laser light. So laser light are far more superior than conventional light sources and LED light. Hence, laser production is essential in our daily life and in the field of science, everything. So let us now know the properties of laser. We come to know after our previous slide that the laser properties can be broken down into four basic properties. We can easily say that laser has high directionality, it has high monochromaticity, it has high intensity, and it is highly coherent. By high directionality means the light being produced by laser follow a certain direction. They have a narrow path and their divergence rate is very low. For example, the conventional light sources have divergence rate of like 1 meter per 1 meter travel, but for laser light sources they have the divergence rate of 1 mm per 1 meter, which is far better than the conventional light sources. If we talk about frequency, the laser light sources and the particles obtained from laser light have same frequency throughout the light production. But for conventional light sources, the frequency of each and every particle is different. So nice quality of light is only possible due to laser. Laser beams are highly intense. This is due to the fact that the number of photons produced per second by laser is in the order of 10 power 16 to 10 to the power 28. This number rapidly decreases to 100 to 1000 in case of conventional light sources. So, for example, the scientific approach to this fact is 1 watt laser beam is much more highly intense than 100 watt bulb. And talking about coherency, yes, laser is highly coherent. Laser is highly coherent because the particles in the laser are of order. They are in phase with each other. Actually, there are two kinds of phase: temporal phase and spatial phase. Temporal phase is phase is phase can be described due to coherency, and there are two kinds of coherency rather: temporal coherency and spatial coherency. Temporal coherency is also termed as transverse coherency, and longitudinal coherency can be known as spatial coherency. So in spatial coherency, what we have that two wavefronts have the same phase at two different spaces at same point of time. Whereas in temporal coherency, we get to know that two wavefronts have same phase at the same time in two different spaces of time. And this is all about properties of laser. And these are the basic properties and most useful properties for any light source. And since laser possesses them, laser is of highly used, and laser is used in daily life depending on these nice qualities. Now let us know emission and absorption. The term emission we got to be familiar with in the first slide. So let us know what emission and absorption stands for. Emission simply means the energy when an atom travels from lower energy level to higher energy level with gaining some energy, it is called absorption. But if the same atom travels from higher energy level to lower energy level with release of certain energy, then it is known as emission. In the first diagram, we see that the atom from its ground state travels to excited state with having obtained certain photons carrying energy Hb. Here H is Planck's constant and mu is the frequency of the radiation, and its energy value increased from lower level to higher level, and hence we can say that in the first diagram energy absorption has taken place. But if we talk about emission in the second video, we can say that atom is traveling from higher energy state to lower energy state with release of certain energy of radiation given by h mu. In this case, we say that emission has taken place. Now to the basic facts about laser and basic principles on which laser depend are emission and absorption, and we can actually relate this absorption, emission Talking about emission, there are actually two kinds of emission: stimulated emission and spontaneous emission. As you know, in absorption, if we provide certain energy to an atom, it goes from lower energy level to higher energy level. Same happens for emission also, but emission occurs sometimes naturally. That means even if we don't provide any photons, it can drop from higher energy level to lower energy level. This kind of emission is known as spontaneous emission. But the emission in which we have to provide certain photon so that the atoms drop from higher energy level to lower energy level, this kind of emission is known as stimulated emission. And using Einstein's relation, we can find out the relation between absorption, stimulated emission and spontaneous emission, which is highly useful for studying laser. So let's begin how to track the Einstein's relation for laser. So in Einstein's relation, the rate of absorption is denoted as R1. This R1 is the number of atoms per unit volume excited from lower energy level to higher energy level per unit time. This R1 is directly proportional to N1 and also directly proportional to E. What is N1? N1 is the number of atoms at ground state, and energy means the energy of the radiation. If we remove the proportionality sign, we get R1 equal to B12 N1E. This B12 is the Einstein's coefficient for rate of absorption. Similarly, in order to find out Einstein's relation, we define rate of stimulated emission and rate of spontaneous emission. Rate of stimulated emission is denoted as R2. This R2 is also proportional to N2 and E. In this case, E is also energy rate of radiation, whereas N2 is the number of atoms per unit volume at excited state. If we remove the proportionality sign again, we get R2 equals to B21 N2E. Here B21 is the Einstein's coefficient for stimulated emission. Einstein's coefficient for spontaneous emission is introduced in R3, where R3 is equal to A21 N2. Here R3 is not dependent upon any energy rate of radiation because R3 is spontaneous emission, and as we have already defined, spontaneous emission does not require any external agency, it occurs naturally. So we are going to be briefly deriving the relation between absorption, stimulated emission and spontaneous emission in our next slide, which is as follows. So I am going to take you through all these equations, and finally we can derive this relation, which is important characteristics of laser, which is heavily used to produce laser. So for deriving in steady state at thermal equilibrium, the two emission rates, spontaneous and stimulated, must balance the rate of absorption, which is defined by this equation. Now in our previous slide, what we defined R1, R2 and R3, we can use this R1, R2 and R3 and drop them here. Now we have to know how does we obtain the condition that satisfy the production of laser. So the condition is population inversion. Population inversion is the state of having more atoms at higher energy level than lower energy level. In normal condition, we know that rate of emission is equal to rate of absorption, but for laser production to take place, we have to get the rate of emission more than the rate of absorption. For doing so, we need the state of population inversion. The process by which we obtain population inversion is known as optical pumping. That means optical pumping is nothing but the process by which we get more number of atoms at excited states so that laser light can be produced. Here we have the two pictures. Here is a normal distribution in which the ground state is having very high number of atoms and the number of atoms consecutively decrease in the subsequent energy levels. But if you obtain population inversion, the number of atoms in the excited state are far more than the ground state, and hence here rate of emission increases more than the rate of absorption, and hence laser production is possible. So there are many ways of obtaining population inversion, meaning that there are many methods of optical pumping, and these methods are briefly introduced as electrical discharge, inelastic atom collision, and optical pumping. So let us introduce and let us briefly define what are these things. So electrical discharge. In electrical discharge, we give a certain high voltage, a very high voltage in the discharge tube, so that the atoms readily get into excited state and they travel in a rapid manner to the higher energy state, and thus population inversion can be easily obtained. In inelastic atom-atom collision, the source of the energy is same as electrical discharge. That is, we have to provide initially a certain energy of high voltage. But unlike electrical discharge, in atom-atom collision, atom-to-atom collision does not have its own atom exciting, but rather the atoms which get charged, they excite their other atoms, their neighboring atoms by collision, and so this is known as inelastic atom-atom collision. There are other methods also like semiconductors or the process where light source is used, which are simpler methods, and they are also used for obtaining population inversion. Now, talking about pumping schemes. Pumping schemes is the way by which population inversion gradually takes place. So there are three levels. There are basically three kinds of pumping schemes: 2 level, 3 level, and 4 level. 4 level is the most convenient one shown in the picture, while 2 level and 3 level are not of such use. Like in 4 level scheme, we can see that the transmission or the laser production takes place by the use of 4 energy levels: 0, 1, 2, and 3. But in 2 level pumping scheme, the energy levels number is only 2, and in that condition, the condition for population inversion, that is the rate of emission being more than rate of adsorption, is very difficult to achieve, since the excited level cannot hold much number of atoms. In 3 level, though 3 level is more convenient than 2 level, 3 level is highly difficult to maintain. So the most convenient one is 4 level pumping scheme. Let us briefly introduce the 4 level pumping scheme. In 4 level pumping scheme, first we provide certain photon to the ground state, and the atoms readily jump from ground state to the excited energy state, that is number 3. From excited energy state, since spontaneous emission takes place and cannot hold the atom for a longer time, it fast decays into energy level 2. From energy level 2, the atoms gradually move to the lower energy level 1, and while traveling from energy level 2 to energy level 1, the laser transition takes place. And after the laser transition has taken place, the atoms again go back from one level to the ground level, and the cycle keeps rotating and the laser keeps forming. So let us at last look what are the components of laser, the types, the uses, and etc. So the basic components of laser are energy source, active medium, and optical cavity. Energy source is any source that is able to excite the medium for the laser production. Active medium is nothing but the medium which gets excited and in which the atoms can move from lower energy level to higher energy level, and then stimulating them, they can move from higher energy level to lower energy level and form laser beams. Optical cavity is the device, we can say, which is used to provide a backdrop for a laser production. This optical cavity is formed by two glasses at two sides, or rather two mirrors at two sides. One of the mirror is highly reflecting, while the other one is a little less reflecting than the first one. This condition is most for obtaining laser in any system. Now let us quickly look at the types of lasers. Types of lasers: we have gas lasers, chemical lasers, dye lasers, solid state lasers, and semiconductor. So what are gas lasers? The laser in which the active medium is nothing but a gas. This kind of laser is known as gas laser. So the common example of gas laser is helium neon laser. In the common example of gas laser is helium-neon laser. In helium-neon laser, we don't actually excite both the atoms, but we excite the helium atom, which in turn excite the neon atoms, and which can go from energy transmission from higher level to lower level, and laser formation takes place. This helium-neon laser is used mostly for holograms such as laser printing. Now, talking about the chemical laser, not the laser system in which we use any chemical for as an active medium. This is known as chemical laser. In this laser, the energy source is certain chemical reaction. These are used usually for mostly for UV. Dye lasers are also very useful. They are used as the lasting medium in the form of liquid solutions. They are used in medicine, astronomy, manufacturing, and many more other uses. The solid state lasers are those kind of lasers which are in solid form, like the gases are in gaseous form. The dye lasers are in liquid solution form, but in solid laser, the medium is in solid form. They are used also for weaponry like chemical lasers. Semiconductor laser is also of regular use. They are also known as laser diodes. A semiconductor laser is one where the active medium is a semiconductor similar to that found in a light emitting diode. Here, the active medium, which we have already talked about previously, is a semiconductor. They are used regularly in telecommunication and medicine. So, hope you liked the video on laser. Hope you were able to give you a certain introduction of laser, and you got to know something more about laser than what you already knew. And thank you so much for watching.